I got my Christmas lights out today, and I noticed this. The LED lights that are in the tungsten style bulb. They were flickering, they were not coming on. It wasn't going well. So I started looking at the string itself. I had this string for about 2 or 3 years, and growing up, I remember as a kid, you turn on the holiday light strands and you would have a light that would blink or flicker, or a set of lights that would be out. It'd be completely out, or half the strand would be out, and you'd wiggle the bulb, and then I would be like wiggling the base and whatever, and sometimes the lights would come back on again and sometimes they wouldn't. But I noticed that this strand was doing it. The single chip version of these, which is just 2 wires, and those have been running for an entire year. They've basically been on pretty much every day for about 6 hours a day, because I use the timer function. So they've gotten way more use than these, even though these are technically 4 years old. The single chip version of these, they've gotten way more use. And so it surprised me that these were having issues after only 4 seasons. And then it dawned on me when I was looking at this particular strand of lights is no different than a traditional tungsten set of light bulbs with a few differences. And so I'll draw out that. So these sets, typically, when they were wired up, they would be, you'd have mains AC, so this is 120 volts. And what you'd have is, so standard set where if you were to disconnect one of the bulbs, then this whole string goes out because you have no current flowing through this loop. But what a lot of manufacturers did was have a configuration that the strings still remained basically the same, but they changed the way that the light was configured. And so the light would have its tungsten filament, and then it would have like a loop around it. And this is inside of its little, this would come down here, have this little leads coming out. I'm sorry, these are actually the leads here. These are actually the leads here, like a, that classic like teardrop thing. Or I don't know what you'd call that, but that little like thing on the top. So if this filament burnt out, it would like get really, really hot. It would melt this wire and it would bridge out the lamp. I'll highlight it in orange. So this part here would bridge out. The filament itself would be gone. You might see like a classic like burn mark or whatever on the inside, but it would keep the set going because you wouldn't break a lamp, because you would have a set of some impedance that's greater than 0 ohms. You'd have this link here, which was about 0 ohms. The trouble with this is that if you had one bulb burn out, not a big deal, but if you had multiple bulbs burned out, then the amount of current flowing through this loop keeps increasing, because we have a known greater than 0 ohm impedance being replaced by something that is approximately equal to 0 ohms. The more that these are being replaced by this approximately equal to 0 ohms as opposed to greater than 0 ohms, the current through this loop keeps increasing and increasing, and eventually you're going to have a dead short across this wire. And so that's why many of these things employed a fuse in line with the plug. You might see a plug, and then you'd have like a door that you'd slide back, and there'd be 1 or 2 tiny little fuses in there sitting down inside this little door. And then you have the plug coming off of there. This is how incandescent bulbs work. And the interesting thing is that this phenomena of like half the strand going out or flickering or any of that stuff, it was noticeable on these strands quite often. And so it surprised me when I was looking at the LED strands, that's this strand right here that I'm talking about before. This LED strand is completely different than this, because it's not mains voltage reference. It's just going to a battery pack. It might be, typically, if you're using alkaline batteries, it would be 4.5 volts. But I use rechargeables, so it's 3.6. These lights are actually configured completely different than the incandescents. Even though they look the same, they're actually configured, I'm going off a little bit off. So you have every LED in parallel in the strand. What you've got going on in the strand is quite peculiar. If you look at it, you have 2 wires going in and then 2 wires coming out, as opposed to what you might traditionally see on a bulb of just like 2 wires and maybe 1 continuing. Because if you have a strand where you can plug them end to end, you might have just a carrier of line going all the way across to go to the plug of the next strand, so you can plug it in and continue the strand. But if you remove that, you would just have 1 wire, because you have the neutral at the end. You'd have 1 wire going in and going out to the next one, and then the single wire just following along all the way to the end of the strand to the last bulb. You can see it in this picture here, right? You'd have 1 wire coming in, 1 wire coming out. So let's just draw it up here. There's the light, and there's this little connector-y thing, and then you have the wires coming out of the bottom, and you may have 1 wire coming in. This is the one going in, boop, boop, like that, and 1 coming out. And then you have 1 wire that's going along. That is your neutral, basically your return path. But here you have the what's going into the bulb and what's coming out. And you have this other line, which if we were to say this is the line, then this is your neutral, going all the way along to the end of the strand. And if we got to the very end of the strand and the last bulb, then this would come in, and then this would go in, and you would see there be nothing there at the end. And then if you had one that had that connection, additional connection to another strand, then you might have a 3rd wire that would be line and then neutral. So it would just come out a node right there. Hopefully that makes sense. To continue down the strand. Okay, so that's the classic 2-wire or 3-wire with the extension outlets. So we'll say they call them like continuous strand or something like that. Continuous. I'll put it down in the lower third if that's how they would wire this thing up. So these LEDs, they have a weird configuration. It doesn't really correlate to any classic or vintage incandescent configuration. Even the more advanced sets that came out later on, they would be divided like into 2 halves, because you'd have like 200 lights or whatever on a strand. All they would do, you'd still have the fuse, you'd still have this connection point. I'm going to come right off here, I'm going to drop down, and we're going to do another row of these in parallel with the original strand. That's all they were doing. And then back to neutral again. Let me draw a little circles for our bulbs. If you pulled out one of the bulbs in these sets, you'd see half the strand would go out. Only half the strand would go out, the other half of the strand would stay lit. On the smaller sets, if it was like less than 50 lights, I think it would just be 1 set. But if you got up to maybe 100 lights, maybe they would split it as 50 and 50. And I think the highest you could probably go was 200, they would split it as 100 and 100. That's pretty much the only parallel configuration that I've ever seen in a tungsten incandescent bulb light sets. This has every single one of them in parallel. If you look at the bulb holder construction, you see that there are 4 wires. If I were to draw that out, you have the same sort of thing. You have this bulb. Instead though, it's an LED. Let me make sure I'm getting the orientation is correct. So there it is sitting in the little capsule, and it comes down here and it has the legs. It's just like, if you pull the bulb out, it looks just like a vintage bulb. It's got the 2 little bent leads on it. But inside, it's not a bulb. It's not a bulb. It's an LED. So this one is just sitting in there with leads coming out, bent back over like it would be if it were a vintage incandescent bulb. And so these come out, and then the leads, they come down, and then they come back out like this. Come down, and then out like this. And I'll highlight it in, we'll do blue. So these are the leads. On the inside of the holder, you can actually see the example. I chewed away one side of it. You can see there's a contact inside there. Contact is on the wall of this. It's on this wall here, and I'll highlight them in orange. And then you have a wire coming in. This is where it gets crazy. Okay, I'm going to draw the wire coming in as black, and the wires going out as red. So you have a wire, actually we'll do line, comes in, or plus DC, and then a line or wire comes out. So this is the positive side, this is the negative side. And then, you know, I just realized I just I'm drawing negative in red. Whatever. Oh man, this is great. So, yep, let's just do this, even though the diode's in the wrong direction. There we go, fixed. This is negative DC. And this is positive DC. And so you can see what's happening here. We have the positive DC down here. So we have this configuration running through all of these lights. We'll just pick one half. This half here. We'll say it's the positive side. Here's what it looks like. And we're getting closer now to what is actually the culprit for why these lights flicker and have issues after only a few seasons of use. And what I see in this construction, so this is crimped in two places. One where there's the insulation to hold the insulation in place, which is good. And then it's crimped again there where the wires come in, the two wires come in. And why this is so interesting and critical for this is that, for the behavior of the lights, is that this wire is stranded copper and this contact is brass. So these are two dissimilar metals, and that's twisted here, and then it's just kind of pressed up against this connection point. Why does that even matter? Well, if I draw this out, so with the wire coming in, it comes in here, it's crimped, and then another wire leaves, right? Just do it in pencil. And then it's wherever it's gray is where it's been stripped. And then it's crimped here again. And then the important piece is that, so this is all brass. So what happens when you have two dissimilar metals that are sitting next to each other with no protection? They corrode. And so this metal begins to corrode or form an oxide layer between the two metals. And what happens is the impedance or the resistance goes up. And so at this point, you start having increased resistance. This is just for one. If we went through a set of 100 of these, they all have the same connection where you have a bare copper to brass interface. And that's only one side of the connection. There are two of these for each lamp, right? So this actually is by two again. So you have 200 connection points on one set of lamps. So if I'm looking at this, here's the actual lamp. And I took out the one side, that's the one I was showing. It's this guy here. But that was originally sitting like this inside that housing. And so as I noticed, and where I had the whole strand, and if I just quickly draw, these are all the same LEDs. And if I look at the whole strand, and I know I drew them in series, it doesn't matter. We're not looking at the electrical connection at all. All I'm talking about is the brightness of the LEDs. So it just went like this. So this is the intensity of the lamps. It was really, really bright at the beginning of the strand, and then just kept decreasing down to where it was like, this was dim, and this was bright. Now, all strands do this. You do have, even if you have the whole strand, let me go back to the previous page. If they have the whole strand wired up like this, you still have a voltage drop. You still have an inherent impedance between each of these lamps. Because this is a piece of wire. It's not 0 ohms. It's some very low amount of impedance. But as you keep going and going and going and going, the voltage across this, if you were to measure across each one of these points, you might get, let's say we're looking at 4.5 volts, just the alkaline cells. You might get 4.5 here, let's say. And then you get down to maybe, let's say this is like the 10th or 15th bulb, maybe you're down to 4.4. And you keep going to the 30th bulb, and you might be down to 4.1, so something like that. And you keep going and going and going. Eventually, you get to the very last bulb, and you might be down to a voltage of something maybe 10% or lower than this original voltage, 3.7. Enough to still light the LEDs, enough to still get good intensity, but the voltage is dropping even if you have even if you have one of these sets, these style sets. Same sort of thing is happening. It's just not happening as obviously. So if I were to take this and measure across that section, okay, so it's the internal impedance of the meter. Oh, it's climbing a little higher. 0.6, 0.5, it's coming back down again. That's basically the internal impedance of the meter. That's fine. But if I were to take the probe tips and go and grab one of these, let me try to get one of these out. Grab one of these, and then we'll get the whole thing over here. Pardon the mess. Grab the first one in the strand, pull its bulb out, and then we'll just grab, this is somewhere in the middle, and then we'll grab one right at the end. So I'm going to go on one side. It's going to be kind of a guess of like which side is which. But if I go to one side, do I get anything? I'm getting mega ohm. I'm thinking it's the wrong side. 12 ohm impedance. That's just wire to wire. No bulb or anything in the way of that. And that's halfway through the strand. And if I go again to the last one, and this is the last bulb in the strand. Okay, we're still at about 12.6, 12.7 ohm. Let's try the other side. Oh, geez. Look at that. 95 ohms, 100 ohm, 105. This is why they were so dim. If I plug all these back in, here's the interesting thing, and I fortunately did this before I had it on video, but if I plug these in, you'll see that they will still light. Well, they get increasingly dim. But if you look at the first bulb on the strand, it's quite bright. And if you look at the last bulb on the strand, so yeah, you can see it right there, how much dimmer it is. So you're always gonna have this shift in brightness to dim when you're dealing with like LED, low voltage stuff. You may appreciate the LEDs are a little bit more dim toward the end of the strand. Honestly, in these newer sets that I've seen that are single strand solid copper wire, they really minimize the impedance drop across the strand. I might do a separate video where I can maybe figure out, just sand off a little bit of the enamel and we can test it. My guess is that these have way lower impedance. Even I've got a set that I just bought, similar to the ones I had bought last year, 66 feet long. And the last LED and the first LED, like you really can't see much of a difference in. If I turn this on, here we go. So there's the first LED in the strand because it's wound around the, and you can see we put the last LED in the strand next to it. I know there's other LEDs around it, but there's not nearly the intensity difference as there was with the style that I showed earlier. If you're looking for low voltage lighting that runs on batteries, on a battery pack, I would avoid this style of lighting, especially any of the ones that have bulbs that can be physically removed, because there's a lot of exposed copper or other metal, whatever, that's in there that's being used to create that connection. I was able to get them to start working again, honestly, by going through each one of them and going like this and just pulling on the wires and moving the connection points, trying to move this a little bit to get it off of whatever the corrosion was inside there, and then it lit up. They started lighting up again. They're still pretty dim. The internal impedance is still pretty high, but they're all basically lighting again at varying levels of intensity. And so if I let this sit again for another year, turn it back on again, I'm pretty sure I'm going to encounter the same behavior. I found this interesting. I never really paid attention to them. I didn't really pay attention to how these things were wired, and I didn't think that they were wired actually and then connected with a physical contact. When I pulled this out and you look at it, wait a minute, this is basically the standard tungsten setup. When you then see the behavior of the lights and see how much they're dimming out and flickering, and you look at this and you see this construction, it makes sense as to why this style for low voltage application, if you see it, I would say perhaps avoid it and go with something like this if you prefer it. If you really do like the style of these bulbs, then by all means, it's for aesthetic purposes. But if you're looking for longevity and the maximum efficiency and long battery run times, then I would probably stick to this style. We put them in the windows and in the tree. I think it's a pretty cool setup. If you like what you saw, give it a thumbs up, and I'll see you all in the next one. Take care.